Hello, colleagues. My name is Yuri Petrov. I'm from St. Petersburg. I represent the Mathematics and Mechanics faculty of St. Petersburg University. I'm going to talk about the fundamental analogy between dynamic fracture and the simplest mass on spring model. Over the last period, I hope to attract your special interest to the experimental and theoretical study of some threshold effects, which, in my opinion, are left unattended. This is an outline of my talk. First, I will discuss the crack initiation problem and corresponding impact fracture effects, mainly the unstable and floating value of the critical stress intensity. Sometimes it exceeds static K1C, sometimes experimenters notice it can be lower. Then we will discuss the incubation time fracture model, which effectively predicts the discussed effects. And finally, I want to show you an interesting analogy, and we will see that fracture of a linear oscillator provides us with the same effects and has a lot in common with the crack initiation problem. Starting with the crack growth initiation, we remember that in statics we can generally agree that in brittle materials the crack starts to propagate when the stress intensity factor reaches some a priori known ultimate value K1C. On the other hand, the situation when dynamic loading is involved can be far more complicated. In dynamics, the critical stress intensity factor value is different. It can exceed or even be lower than the K1C value. And sometimes it is very, very unstable and depends on the rate, duration, and the way of loading the same material. This phenomenon was discovered in numerous experiments like those by Shoki, Kaltkov, Homma, Ravichandar, and other researchers. And it was and still is a matter of numerous discussions about the nature of dynamic fracture toughness. All these instability effects can be explained on the basis of the powerful incubation time fracture model, when it is assumed that fracture at point x and in time t takes place if this inequality holds. The criterion also contains two other parameters, d and tau. The d parameter specifies considered scale level of fracture. The fracture at the selected scale is regarded as a result of particular relaxation processes caused by multiplication of micro cracks and the coalescence. The incubation time can be understood as a characteristic time of relaxation. Here, the fracture process is quantized. Since we introduce both characteristic size and characteristic time of the fracture process, it is important that both parameters are related to the given scale level. Now, I'm going to use a simplified version of this criterion, which deals with stress intensity factor function. This version is applicable for the crack initiation problems only and should not be used for crack propagation studies. Now I consider a particular boundary problem of the crack loaded with the impact, let it be a short pulse. Consider an infinite plane with the semi-infinite crack loaded with the pressure pulse. The problem can be formulated using well-known potential-based wave equations with appropriate boundary and initial conditions. We solved the problem of the sudden application of constant pressure to the crack faces. In this case, the load is described by a Heaviside step function. This is a very important case since the solution of this problem further can be used to obtain a solution for an arbitrary load using the convolution integral technique. After analytical analysis, we see that according to the incubation time model, the fracture can occur at various stages of stress intensity history. We see a great variety of possibilities. Depending on the pulse characteristics, the starting stress intensity value can be less than, equal to, or exceed the static K1C. The decreasing stage is of special interest. The fracture takes place when the current stress intensity factor starts to decrease, and it was firstly noticed in experimental works by Shoki and Kaltkov. We can use the incubation time criterion to analyze two representative cases, fracture with maximal fracture time and therefore maximal delay, lower curve, and the case when there is no delay and fracture time equals the load pulse duration t, upper curve. For each amplitude value A, we can look for a corresponding critical stress intensity factor value, leading to either delay or no delay cases, and this way we construct two curves. As you can see, the maximal delay curve is below the static fracture toughness. It is also interesting to construct the dependence of the load momentum of the pulse amplitude. The momentum is simply a product of the load pulse duration t and pulse amplitude a. Again, we can consider two situations: the maximum fracture time case equal to the maximum fracture delay, and the no delay case when the fracture time equals the load pulse duration. Obviously, the lowest pulse momentum is required if we allow the fracture delay, the lower dashed curve. This is generally an optimal situation, but it is probably hard to implement experimentally. It is practically much easier to apply the load and to wait till the fracture occurs, meaning that we are in the no delay situation, which is described by the upper curve. But the no delay upper curve also appears to have a minimum providing optimal load momentum with the lowest value. It can be important for the fracture process optimization needed for industrial applications. At least it is very important to be aware that the optimum does exist. And now I come to the next point of this work. One of the most interesting things related to this model is the existence of a fundamental analogy between the above-mentioned results and the behavior of a linear oscillator. Now let's turn to a seemingly completely different problem, which I will prove appears to be surprisingly similar to the just discussed crack problem. Consider a linear oscillator subjected to two load types, a linearly rising load and short pulse loads. These two load types can be used to study two dynamic fracture effects: the dependence of the system strength on the loading rate and the fracture delay case, which is of the highest interest for us now. First, let's have a look at the rising load problem. For such a simple system, we can easily solve the motion equation to obtain the dependence of the mass position on time. Further, this solution can be analyzed using a very simple fracture condition. The spring breaks when critical elongation xc is reached. For different rates alpha, we can calculate corresponding critical load force values at the fracture moment. It appears that for the lower loading rates, the critical force equals the static critical force at the fracture time. But for high loading rates, the critical force exceeds significantly the static critical value, providing a so-called dynamic branch of the strength rate dependency curve. This result can easily be proven by the solution analysis. Now let's consider the short pulse load. The oscillator is loaded with the force pulse with duration t and amplitude a. Again, we easily obtain the motion law for the mass by solving the corresponding differential equation. Using the same critical elongation fracture condition, we can construct the dependence of the load pulse duration t on the fracture time t star for a fixed pulse amplitude a. The constructed curve clearly shows the fracture delay phenomenon, and two representative cases emerged. The no delay case, when fracture time t star equals the pulse duration t, it is a vertical line here, and the maximum delay case, when the fracture occurs after the load disappears. For these two cases, we also can obtain dependencies of the fracture pulse duration on the pulse amplitude on the left. Now, when we have dependencies of the amplitudes on the durations for the fracture pulses, we can explore the momentums of these loads. The load momentum is the product of the amplitude and duration. And on the right, you may see dependence of the fracture load momentum on the load amplitude for both cases, no delay and maximal delay situations. The upper no delay curve appears to have a minimum which provides optimum fracture load in terms of momentum. And it looks absolutely identical to what we had in the crack initiation problem. Now just let's put our crack growth initiation problem and spring breaking problem in one slide. The momentum versus amplitude dependence appears to be nearly identical, providing minimal points for the no delay situations. We can see that the crack appears to behave very similarly to the mass on spring when subjected to pulse loads. Both rate dependencies and delayed threshold phenomena can be found and juxtaposed in these two seemingly different problems. The existence of optimal characteristics is also predicted in both cases. Obviously, the threshold situations should be studied more carefully in fracture dynamics, which is not done yet nowadays. So we have a very beautiful analogy which emphasizes the fundamental nature of the phenomenological approach, predicted numerous effects by taking into account the preparatory incubation process. The analogy gives me a possibility to analyze some well-known experimental observations based on the oscillatory model. How we can do it, oscillatory speaking. We will consider two works by these authors. In both cases, we suppose that cracks are either long enough or the load duration is short enough so that the semi-infinite crack approximation should be applied. We will try to fit experimental points by theoretical TA curve using the incubation time criterion, and thus we evaluate the incubation time. Then we use this curve to build dependence of the load impulse on the load amplitude. As we have shown, this dependence for the zero delay case has a minimum for both crack and oscillator problems. And this minimum can be used to match these two models and to finally calculate parameters of virtual oscillator which corresponds to the crack. Let's turn to the first set of experimental results. In the experimental works by Shoki, Ehrlich, Kartkov, and Homer, steel specimens with relatively long cracks were loaded by an incident rectangular pulse, and for 3 fixed pulse durations, threshold amplitudes were registered. This way, the authors provide 3 points of a TA max delay or threshold curve, which can be used to evaluate the incubation time. On the right, we show the zoomed-in version of the graph, which clearly indicates that fracture delay could not be registered for the used pulse durations. The load pulses were too long, and much shorter loads should be used in order to register fracture delay in this particular setup, around 5 microseconds. Anyway, theoretical TA curves for both threshold case and zero delay case was constructed for these experiments for 40 steel. The constructed TA dependence can be used to build the critical momentum dependence on the load amplitude. As expected from our previous calculations, the zero delay curve has a clear minimum providing optimal in terms of pulse loading regime for fracture with no delay. Once this minimum is calculated, the obtained values can be used to calculate parameters of the corresponding virtual oscillator. We simply suppose that this minimum coincides for both models. In this particular case, we are not able to fully adjust the virtual oscillator parameters. We cannot find mass and spring stiffness, but we are able to evaluate the oscillator eigenfrequency. And for this material problem, this frequency turns out to be about 280 kilohertz. The same can be done for polycarbonate. The eigenfrequency turned out to be about 400 kilohertz. A good difference for polycarbonate is that the pulses were short enough to register the delay. My conclusions can be summarized in this picture of a black box coupled with the pulse load. The incubation time criterion for cracks has a simple mass on spring interpretation. Fracture delay and various initial critical stress intensity factors can be predicted, and there is no need for material functions. There is an optimal input momentum for the practically convenient no delay case. Crack behave similarly to oscillators exhibiting mass and stiffness which can be evaluated. The analogy emphasizes the fundamental importance of the experimental study of the threshold situations which are still unattended. Thank you.